Great, welcome everybody to our usual Tuesday seminar. It's a great pleasure to have today Nina Kamčev, who used to be a long time ago in Zurich and now kind of giving talk at our seminar. And she will talk about canonical colorings and random graphs. Please.
Thank you. Thank you for organizing the seminar and for inviting, and thanks everyone for coming. It's a pleasure to be here. So please ask any questions during the talk. The topic today is canonical colorings in random graphs, or the canonical Ramsey theorem in random graphs. And some results I'll mention are joined with Matthias Schacht. So let's start with the usual Ramsey's theorem in random graphs. So actually, let's start with the usual Ramsey's theorem. So what we let an adversary color the edges of Kn, say red and blue, and we want to find a monochromatic copy of KL. And now, for a given L, if this N is large enough, we are guaranteed to find the monochromatic copy of KL. So this is a kind of robustness property of the complete graph. So if an adversary partitions the edges, we are still guaranteed to find the monochromatic copy of KL. And a very fruitful line of research is trying to replace this complete graph Kn by something sparse. And you can choose your favorite notion of sparsity, but in our case, we will replace this by sparse random graphs, and we'll try to minimize the density of these random graphs. So perhaps the first definitely classical result in this direction is from 1995. So Rödl and Ruciński showed that with a specific density, the random graph G and P with high probability has this Ramsey property. So don't worry, I'll explain it in detail. But first of all, our host graph is G and P. So we have n vertices, and each edge appears independently with probability P. And this P can be a function of n, and it usually is. And the property of interest is this robustness. So any two coloring of the edges contains a monochromatic copy of KL. And we want this property to hold with high probability, so with probability tending to 1 as n tends to infinity. We're interested in minimizing the density, or rather we're interested in the threshold. So when P equals 0, you just have an empty graph, so you definitely don't have the property. When P is 1, you have the complete graph, so you do have this property. And this property is, by the way, monotone. So if you add edges, then you preserve the robustness property. So as P increases from 0 to 1, somewhere there is a threshold, you will start seeing this property with high probability. So once again, just to emphasize here, n tends to infinity. So we're not interested in minimizing n. N tends to infinity, and we're trying to minimize the density P as a function of n. And Rödl and Ruciński showed that at this density, you can have the Ramsey property. And in fact, this is optimal, but we'll see that later. Before discussing this in more detail, let me first see if there are any questions, because it's important to understand the statement for the talk. And also, I'll just take a step back and give you a little bit more background on this line of research. So this is a certain Ramsey type statement about random graphs, and there's actually a whole field of research on extremal and Ramsey results in pseudorandom graphs, and also in pseudorandom sets of integers. So I will not mention any kind of comprehensive list of results, because again, there are many beautiful approaches. But let me just mention two papers. So first of all, on extremal results in graphs, people have done a lot of work on specific theorems. So there's Ramsey's theorem, Theorem's theorem, removal lemmas, etc. And this kind of culminated in the proof of the KLR conjecture. So the KLR conjecture allows you to use the sparse regularity method in this setting. So the regularity method in dense graphs is very powerful and very well developed. But for sparse graphs, the problem was that we don't have corresponding embedding theorems. And the KLR conjecture is a corresponding embedding theorem and is used with the kind of techniques that I'm talking, is proved with the kind of techniques that I'm talking about today. And the KLR conjecture actually gives a very cheap proof of many of these results, such as the Ramsey theorem that I stated above. But again, it came much later. And another very influential paper is the Green-Tau result on arithmetic progressions in the primes. So here, I'm not trying to compare our results to Green and Tau in importance or complexity. I just wanted to emphasize this fact that it's actually a result about pseudo-random sets. So what they actually show is that pseudo-random sets, according to a suitable definition, of course, of sufficient density, contain long arithmetic progressions. But now the primes are actually a pseudo-random set of density roughly 1 over log n. So the statement about primes actually follows from the statement about pseudo-random sets, which is, of course, very deep and difficult. I just wanted to emphasize that this theorem is actually about pseudo-random sets. And in fact, Green and Tau used some important transference techniques that later inspired the work of Conlon and Gowers on random and pseudo-random graphs. Okay, so that's just a little bit of background, but let's go back to this theorem of Rödl and Ruciński. So let me give you an intuition on why this threshold is optimal. So obviously, in order to robustly contain copies of KL, first of all, you need to contain copies of KL, but you also need to contain them with a significant overlap. So I'll give you an intuition about the lower bound, so about the negative statement. I'm claiming that when P is a small constant times this threshold, then you can have a coloring which avoids monochromatic KL copies. And why is this the case? Well, the crucial quantity to consider here is the average number of KL copies containing each edge. So this average number is just the total number of KL copies divided by the expected number of edges. And this turns out to be exactly the constant to the power L choose 2. So this is how this threshold is actually chosen. And now, when this is less than 1, then, okay, an average edge is contained in less than 1 copy of KL. So now if we pretend for a bit that each edge is in at most 1 KL copy, so if each edge is in either 0 or 1 KL copies, then a greedy coloring does the job easily. So then you can order the edges arbitrarily and color them one by one. And when you want to color some edge E, you look at the unique copy of KL containing this edge. So maybe all edges in this copy so far are red, and then you color your edge blue and vice versa. So you use each edge in order to prevent the corresponding monochromatic KL copy, and that's it. However, this is far from the truth, this if, and actually that makes the problem considerably more difficult. These exceptional edges that are contained in many KL copies, there are very few of them, and they're far enough in the graph. So you can actually make this argument rigorous, but it is difficult. So if these exceptional edges are far enough, then you can have a coloring in a way that they don't conflict. And then that gives you a 2 coloring with no monochromatic KL copies. Okay, so usually we call this positive statement the 1 statement, and the negative statement the 0 statement. And in this talk, we'll be concentrated on the 1 statement, so the positive direction. But again, an interesting thing about this problem is that neither direction is easy. Okay, so what is our question for today? Well, our question is, what if we give the adversary has no restrictions on the coloring? So in the Rödl and Ruciński theorem, the adversary can only use 2 colors, and this actually extends to an arbitrarily bounded number of colors. But now, if you say the adversary can use any coloring, any number of colors, no assumptions on the structures, what kind of KL copies are we guaranteed to find? So first of all, this problem is not at all obvious in the complete graph. So let's move back to the complete graph and see what we can find in an unrestricted coloring of a complete graph. This is the so-called canonical version of Ramsey's theorem, which you may be familiar with, but I'll introduce it gradually. So it's a famous theorem proved by Erdős and Rado. Okay, so let's say you want to list all patterns of KL coloring that you can find in an arbitrary edge coloring of Kn. So first of all, you have to have monochromatic or rainbow copies, because the adversary can use just 1 color for all the edges or a different color for all the edges. So, okay, maybe then you try and prove a theorem in this form, and then very quickly you'll realize that it's false, because the adversary can also use this type of coloring, which I refer to as a min coloring, because each edge is colored according to its starting vertex. So this kind of coloring does not contain monochromatic or rainbow copies of KL. So we need to add these type of copies to our list. Okay, so we need to contain possibly a min colored copy of KL, or also a max colored copy, which is just a symmetric version of that. And it turns out that now this is a complete list. So actually, in any coloring of the complete graph, you can find one of these copies of KL. And for brevity, we refer to these as canonically colored copies of KL, so any of these 4 patterns. Okay, so we saw that Ramsey's theorem has its variant for random graphs. And now Matthias and I and some authors earlier were interested in when can we extend this canonical version of Ramsey's theorem to random graphs. So what would this statement look like? So first of all, notice that this is stronger than the usual Ramsey's theorem, meaning that the threshold for this has to be higher than at least as high as the threshold for Ramsey's theorem. This is because you can always use a 2 coloring. So for random Ramsey's theorem, we saw that below the threshold, there is a 2 coloring, which avoids monochromatic KL copies. But then if you use this 2 coloring in the canonical setting, this 2 coloring certainly will not contain rainbow or min colored or max colored copies. So this coloring shows you that the threshold for canonical Ramsey has to be at least as high. And then the question is, does the corresponding 1 statement also hold? And this is what Matthias Schacht and I showed. So above this threshold, with high probability, any edge coloring of GNP contains a canonically colored copy of KL. But for the rest of this talk, I'll just give you a snippet of the proof of this theorem. And And in doing so, I have to tell you a little bit about how you would prove the statement for complete graphs in the first place. So for complete graphs, the classical proof uses 4 uniform hypergraphs, and it's very nice. So you can try and prove it using 4 uniform hypergraphs in the corresponding Ramsey's theorem. However, of course, in this random setting, passing to hypergraphs would destroy us immediately. So I need to show you how what's an alternative argument for the complete graph, and then try and translate that to the random setting. And I will also try and present this tool of transference that's used by Conlon, that's developed by Conlon and Gowers, because we heavily use it in the proof of our theorem, and I think it's very interesting and not so often used in the context of graph theoretic results. But before going into the proof, let me point out an interesting corollary of our result. So more or less straightforwardly from our proof, it follows that you have graphs which are canonically Ramsey for KL, so they have this canonical Ramsey property, but they don't contain any copies of KL plus 1. So this is a Folkman type result. In one hand, you have to have heavily overlapping copies of KL, but they never create a copy of KL plus 1. Okay, so I'll go into the proof of this theorem a bit, but beforehand, let me convince you why it's difficult and interesting, and why you cannot just apply these powerful techniques that are already known. So one reason that it's difficult is that it covers 2 extreme cases, and both of these cases are not trivial, and people have worked on them before. So in other words, the adversary can use at least 2 completely different strategies. First of all, the adversary can use a bounded number of colors. So then we're back to the Ramsey problems that we've already discussed. So this is the setting of Rödl and Ruciński theorem. Well, the good news about this case is that we have a number of powerful methods to address them. So there's this more combinatorial multiple exposure method, and then the analytic transference method of Conlon and Gowers, and the ubiquitous container method. But then the adversary can also choose to use a huge number of colors. So for instance, they can use a proper coloring of GNP, and you need to decide what to do in that case. So in that case, you're aiming for rainbow copies of KL. And these are the so-called anti-Ramsey problems. So you have a coloring with certain local restrictions, and can you find a rainbow copy of KL? So our specific restriction is the maximum degree in each color. So we assume that each vertex in each color has degree at most delta, and can you then find a rainbow copy of KL? And this problem has been previously looked at by a number of authors. And in this combination of papers, they found the correct threshold for the anti-Ramsey property when delta, the maximum degree, is bounded. So even when delta equals 1, this is not trivial, because you have a proper coloring of GNP, and you need to find a rainbow copy of KL, so you need all edges of different colors. But indeed, it holds for delta equals 1, and in general for some bounded constant. And the methods are very different from the methods that we see on the right here, so they're constructive. Okay, so in fact, as I said, for both of these problems, the correct threshold is this thing. So this means that the adversary can use any of those strategies. So the adversary can go for an unbounded number of colors, or just 2 colors, or many things in between. And that's part of the difficulty of the problem. And as part of our work, we actually had to strengthen this result to delta being some small constant times Pn. So this is a stronger result than the above because a larger maximum degree is a weaker restriction and therefore gives you a stronger theorem. And this implies, in particular, that each vertex sees at least 1 over delta colors. So each vertex sees only a bounded number of colors. So this is clearly optimal up to a constant factor. Okay. So for most of the talk, I will actually concentrate on this left-hand case because it's actually simpler. But it's already a nice and simple application of the transference method, and that's what I'd like to show you. But before going into that, again, notice that the adversary can use any of those things, but also some curious combination of both of those. So the difficulty is in deciding on the case distinction. So in which case, for which colorings are you trying to find monochromatic copy or a rainbow copy or a min colored or max colored copy? So for instance, the adversary can use this L-1 partite blue coloring. And this means that the majority of the edges are colored blue, but these edges are completely useless for finding monochromatic copies of KL. So you cannot just say, let's look at the majority color or some such thing. And that makes it difficult to apply sparse regularity or any related methods. Okay, so let's have a look at this bounded degree setting. So just as a reminder, a coloring is called delta bounded if the maximum degree in each color is delta. And in these colors, we want to find a rainbow copy of KL. So let's see first how this works in complete graphs. In complete graphs, it's actually very simple. So we claim that in a delta n bounded coloring, where delta is a sufficiently small constant, you can find a rainbow KL copy, but actually more strongly, most KL copies are rainbow. So rather than a constructive proof, so rather than trying to find rainbow copy, we will try to upper bound the number of bad copies of KL. Okay, and how do we do that? Well, first of all, this is just a small technicality. We will partition the vertex set of our graph into L parts, and you can think L equals 5 for the purposes of this talk. Nothing really changes. So we partition into L equal parts. And then we'll be only looking at transversal copies of KL. So only the copies that use one vertex for each part. So whenever I say KL copy, I mean a transversal KL copy here. Okay, and we're claiming that if your coloring is delta n bounded, then the proportion of bad or non-rainbow copies, if it is at most delta. And again, throughout the talk, I'll be talking about the proportion of KL copies because we don't really care about this normalization into the L. Okay, so how do we see that this is at most delta n? So let's first focus on 4 specific parts. So V1, V2, V3, and V4. And look at the copies which have the same color between those 2 pairs. And specifically, let's look at the red color, where red is some chosen color. So we claim that the number of such copies with 2 red edges between these 2 pairs of parts is at most delta squared. And that's just easy counting. So you fix 2 pairs of edges, and now the number of KL copies that extend this pair is at most this V1, which is the size of the parts, to the power L-4. And then you have delta V1 squared choices for the first edge, and delta V1 squared choices for the second edge. And altogether, this gives you a delta squared proportion of the copies. And now, so we were only looking at a single color, say red, and now we can sum or take a union bound over all the colors. And then from there, we get an extra 1 over delta for the number of colors. And finally, we chose the specific configuration of parts, but then summing over all the possible L parts, we get an extra factor of L to the 4th, but this is unimportant because delta, again, is a small constant compared to L. So making delta small enough, this is actually a negligible proportion of all the KL copies. So we showed that the number of non-rainbow copies is small, therefore we need to have at least one rainbow copy. And I want to emphasize this bound, order of delta squared, that works for dense graphs, because again, in dense graphs, you can use this trivial upper bound on the number of copies containing any pair of edges. Spoiler, this part will fail in GNP. So, okay, let's now go to GNP and try and emulate the same kind of proof. So, well, the P will always be roughly at our threshold. So for now, this is not very important. So now what we'd like to show is that a delta Pn bounded coloring, so this is again at most delta proportion of edges in each color around the vertex, contains at most a delta proportion of non-rainbow KL copies. And notice this factor of P to the L choose 2 now, because the expected number of KL copies in this configuration is roughly N to the L, P to the L choose 2. Okay, so if we now naively try to just imitate the same proof, so we fix 2 red edges, and we try and upper bound the number of KL copies containing these 2 edges. But the problem is that these 2 red edges can actually be contained in many KL copies. So this is by no means concentrated in the random graph. So actually, the best bound or one bound that you can write down is trivial and useless. So you can, for 2 fixed edges, you upper bound the number of KL copies by this trivial factor. And then you have delta P proportion of choices for the first edge and delta P proportion for the second edge. But here, the problem is that, let me just find a pen. The problem is that we are missing a crucial factor that we would like to have. Okay, sorry, my annotation doesn't work. Okay, so there's a crucial factor that we would like to have here, which is P to the L choose 2 minus 2. And we cannot get this factor using any kind of elementary counting. So indeed, this is the average number of KL copies containing any 2 fixed edges, but we cannot claim it for some desired fixed edge. And in fact, indeed, the adversary can find 2 edges that are contained in many KL copies and color exactly to those 2 edges red. Okay, but now a natural idea that I've already spoiled, a natural idea is to actually look at all edges of the red color. So well, now we just don't fix on 2 of them, but we look at some delta proportion of edges on the left and on the right, and we try to claim that now these edges kill at most delta squared proportion of KL copies. And now this is a reasonable thing to expect, but definitely not easy to prove. So let me just develop some notation for this problem that we are facing. So we fix a delta proportion of edges on the left and on the right. And in the rest of the graph, we just have all the edges of GNP. So this gray represents all the edges of G and P. And now this is some subgraph of G and P. And we're interested in the number of KL copies contained in this subgraph. And we'd like to have this kind of upper bound. Okay, so here's the notation. So for an arbitrary graph G, we denote by lambda L of G the proportion of KL copies contained in this graph. So we're just dividing by V1 to the power L to focus on the proportion of KL copies. So for example, in the random graph itself, this expected proportion of KL copies will be P to the L choose 2, because each specific L tuple will form a clique with probability P to the L choose 2. And now the statement that we would like to show is that if F is a subgraph of G and P with certain density restrictions, then we can bound the number of KL copies. And the density restrictions are what I mentioned before. So you have at most delta proportion of edges in F on the left, and at most delta proportion on the right. And in the remaining parts, you have no restriction. Okay, but now the important thing is that this F is chosen by the adversary. So this F should be any subgraph of G and P. And therefore a natural choice would be, or natural approach would be to bound the try and find an upper bound on the probability that this is too much, that you have too many KL copies, and then take a union bound over all the possibilities for F. But this is, of course, this is well known to be hopeless. So it's the well-known upper tail problem in GNP. It's known that the number of KL copies can deviate too much from its expectation. So you cannot possibly hope to take any kind of union bound here. And actually, that's one reason, not the only, but that's one reason we end up using transference, because a lot of the standard methods in these extremal problems in random graphs, they give you a lower bound on the number of your desired subgraphs, but not an upper bound. But that's where this transference comes into play. So very, very vaguely, it tells you that we can replace our given subgraph F by some dense approximation. And we've already seen that in this setting, dense graphs are very easy to deal with. Okay, so how does this work? And now we go into the very vague part of the talk. So please ask questions if anything on the following slide doesn't make sense. So we start with F being a certain subgraph of G and P. And now this transference method, it gives you a dense graph F tilde. So F tilde is a subgraph of Kn. But here it's actually useful to work with weighted graphs. So we put a weight on P of P on the edges of this dense graph, because that way we can compare the edge density in F tilde or in P F tilde to the edge density of F. So without this P factor, F tilde would be some dense graph, so positive density, and F would be some graph of density roughly P, and there would be no way to compare that. But this weight is just there to make them kind of comparable. And kind of illustrative way of thinking about that is the following. So think of F as a weighted graph again. So F has weights just 0 and 1. It has very few edges, roughly Pn squared edges, and these edges have weights 0 and 1. And then you can think of this model P F tilde as smearing the edges of F. So what you're doing is distributing the weight from the edges of F to a much larger number of edges, but the weights are now much smaller. So the weights are now 0 or P. Okay. So what does it mean that this P F tilde is an approximation for F? Well, first of all, it means that they have roughly equal number of edges, but much more importantly, it means that the number of KL copies in this graph F is roughly the same as the number of KL copies in P F tilde. Okay, so now if these two hold, we say that F tilde is a dense approximation for F. And notice that this thing on top, it's really just directly related to the graph F tilde. So we can write this number of KL copies in P F tilde as P to the L choose 2 times the number of copies in F tilde, because each KL copy in here contributes a weight of P to the L choose 2. And similar for the number of edges, so we can just take out this factor of P. So the transference is what's going to gain us this important factor of P to the L choose 2. Okay, so again, feel free to ask any questions about this, because I know it's rather vague. But let me now give you a slightly more formal statement. So this is in the form proved by Conlon and Gowers, Samoti, and Schacht. So what they showed is that for your desired accuracy of approximation, the random graph G and P has the following property with hyperability. For every subgraph F of G and P, you can find this dense model so that the proportion of KL copies is roughly the same. The number of edges in the two graphs is roughly the same. And third, stronger property is that they're also close in edge distribution. So if you have more experience in this is just the cut norm. So these two are close in the cut norm, or rather for any two vertex sets of linear size, the density of edges in this object and in this object are roughly equal. So yeah, if that theorem looks too good to be true, then you're probably understanding something, because when I first saw it, I was also really surprised that something like this can hold. So let me emphasize a few important things about the statement. One of them is this for every. So this holds for every subgraph of G and P. So there's no need to take any kind of union bound or calculate probabilities. The second is this with high probability. So this does not hold for every graph or every graph of density P, but you're actually conditioning on certain nice properties of G and P. So that's part of the difficulty. You need to find nice, smooth properties of G and P, which guarantee that you can find such an approximation. Okay. And now, yeah, I hope the statement makes some sense. And by the way, all of these, well, this closeness is measured in a certain by a certain norm that Conlon and Gowers construct, which is also useful for us. And this norm is then, with this norm, you can use some analytic tools like the Hahn-Banach theorem in order to find your desired dense approximation. And the third thing, another important thing that I forgot to mention is this threshold. So this approximation only exists above the threshold. Below the threshold, you cannot hope for such a statement. Okay, so how do we apply this transference statement in our setting? Well, remember the problem was the following. You have a certain subgraph F of G and P, and you have a restriction on the densities of this subgraph between the different parts. And you want to bound the number of KL copies. And here's how you do it. Well, first of all, you have to assume that the GNP satisfies this transference property that I mentioned. So this happens with high probability. And now, assuming that this does hold, you find a dense model for your favored subgraph F. And now, with this dense model, I mentioned that it has roughly the same distribution as our initial subgraph F. So this means that in this dense graph, you have at most a delta proportion of edges on the left and at most delta on the right. But now comes the crucial part that we saw on the previous slide. In this F tilde, you can use a trivial upper bound on the number of KL copies. So just by counting, you can you show that the number of the proportion of KL copies in this F tilde is bounded by 4 delta squared. And then you can translate this back to the graph F and to an upper bound on the proportion of KL copies in F tilde. So you obtain this crucial factor of P to the L choose 2, and you conclude that the proportion of KL copies in F is at most delta square times P to the L choose 2. Okay. Does this argument make sense? So it's very reminiscent of how you usually use regularity. You gain some information on your approximation, you find some useful structure in your approximation, and then you translate that back to the initial graph. Okay, so just going back to how we finished the proof of this bounded case. Well, now we found that the proportion of KL copies with these two edges in fixed red color is order of delta squared, but then we just sum over all the colors and all the parts, and we get this initial constant of 1 over delta times L to the 4th. And here I'm cheating in at least 2 important points, so you can ask about those. One important cheat is this 1 over delta. So it's not actually true that we have at most 1 over delta colors. We can have some very small colors, but this is actually the most difficult case. So the most difficult case is when you have 1 over delta colors and the delta proportion of edges in each one of them. And then it's not too difficult to reduce to this specific case. Okay, so now we roughly know how to do bounded colorings, and that's all I'm going to say about that case. And let me just give you a little bit of intuition for what we do in general. So for the general proof, we go back to complete graphs first to understand what's happening in the complete graph. So how do you prove the canonical Ramsey theorem in the complete graph? Well, we know that there's a vertex with at least delta n edges in the same color, let's say green. Otherwise, you use the bounded degree case. But then inside this green subset, you know the same thing. Otherwise, again, you use bounded colorings. And you use this iteratively, so you find a sequence of vertices with a linear proportion of neighbors in some specific colors. And now if you do that enough times, specifically L squared times, you will find either L times the same color or L different colors. And this will then give you either a min colored copy of KL or a monochromatic copy of KL, modulo some cheating, but that's the main idea. Okay, but let's try, so this now we understand the whole proof for complete graph. And now going back to the random graph, we notice that this proof has some serious difficulties. So first of all, in the random graph, your neighborhoods are of order MP. So you cannot possibly hope to take a single vertex and pass to its neighborhood, because this neighborhood will be way too sparse and then you're immediately dead. Another important difficulty is that this proof uses cliques of size L squared in the complete graph. And that's, again, something that you cannot find in GNP at the corresponding density. So some serious new ideas are needed to imitate this proof in G and P, and we do that by iterated applications of this transference tool. So that would be it for the proof. So just to recapitulate, so we identified the threshold for the existence of, for the canonical Ramsey property for cliques in the random graph. But then there are at least two natural questions. So first of all, you could try to replace this clique by an arbitrary graph H. And the threshold is actually known for the usual Ramsey's theorem, but the canonical Ramsey stuff does not work straightforwardly. Alvarado, Kohakawa, Morris, and Mota can know how to prove it for even cycles. And some of our proof ingredients actually work in general, but there are some technical difficulties with this transference technique. And then also you can think of asking the same question for hypergraphs, and a canonical Ramsey theorem for hypergraphs does exist. And actually, there is a proof for R-uniform hypergraphs, which uses only R-uniform hypergraphs. So there is some hope in translating that to random graphs, but it's far from obvious. Okay, that would be it for me for today, and thank you for your attention.
Okay, great. Thank you, Nina. So maybe let's give Nina a round of applause. Questions? Actually, maybe let me start, and then maybe encourage other people. So this last proof which you were showing us, so it's clear maybe how you can move from sparse setting to dense setting because of transference. But the fact that you don't have KL square, it's really even in a dense case. So even when you move to dense case, you can be somehow blob of KL with a pseudo-random graphs instead of edges, right? You somehow cannot use the fact that you have larger copies, right? Am I correct? Yeah. So then somehow yes, you need to redo this proof, which before you did it in complete graph, and somehow maybe L-partite nice dense graph, right?
Yeah.
What's happening there?
Yeah, good question. So what's actually happening is that you do this, like you build these nested neighborhoods in your dense model iteratively. And then as you're building it, you need to do some case distinction, so some cleaning. You need to somehow distinguish in which case you have a large degree in a specific color, and in which case you have many different colors. But then actually, it's not so difficult. So on the surface, it looks difficult, but it's not so difficult because then you don't really care about the KL squared. What you care about is the sequence of colors. So you find some large sequence in your dense model, and you find some sequence of colors. And then when there is a subsequence of colors that you like, let's say you find L vertices which all send the blue color forwards, then you just focus on those L vertices. And you say, in the dense model, this has a large number of KL copies, and then these KL copies are all that we care about. We don't care about the other L squared parts.
Okay. More questions?
If you wanted to do, for example, canonical van der Waerden theorem in a random set of integers, would this, some of the proof of that seems easier. So it's the proof of the ordinary canonical van der Waals theorem is easier. So is doing it in the random setting also easier?
Yes, yeah, I think it is, because really, so canonical van der Waals would mean either you have a monochromatic subsequence or a rainbow subsequent arithmetic progression. So no min-max stuff. So all you need to do is upper bound, like under the assumption that you have a certain bounded coloring, you need to upper bound the number of non-rainbow ones. And then you encounter a very similar difficulty that we have in graphs, that you cannot focus on a single number and say, now I'm going to upper bound the number of progressions containing this specific number, but you need to use kind of a more global approach. And there actually transference works very well, but there might be other tools that you can use as well.
Yeah, thanks.
Okay. More questions? So if there are no more questions, let's thank Nina again for a beautiful talk. Thank you. Yeah, so that's all for today. We can stop recording.